Then redox stability in water. So water is undergoing a reduction of water under 1 molar acid. It will show a 0 volt, and at a neutral condition, so it is minus 0.414 volts, and then 1 molar base, it is minus 0.828 volts. So the minimum reduction potential necessary for the reduction of water to hydrogen, that is 1 molar acid solution with under 0 and it is neutral minus 0.414, it is greater than the electrode potential, and the 1 molar base solution, that is minus 0.828 volts. Then oxidation of an water. So in 1 molar acid, once again it will show a positive sign here, positive 1.229 volts, and a neutral solution positive 0.185 volts. Then in 1 molar base, it is positive 0.0401 volts. So the minimum reduction potential required to oxidize water to oxygen. So hydrogen in reduction and then oxygen in oxidation, that is 1 molar acid solution with less than 0.185 volt than the standard electrode potential, and a neutral solution positive 1.229 volts. Then 1 molar base solution with positive 0.401 volts. Then the reaction of metal with water or aqueous acids are usually the oxidation of metal by water or hydrogen ions. Then this is favorable for some S and transition of metal group 4 and then 7. Only few oxidizing agent can oxidize the water to give O2, and the greater than positive 1.23 volts for a couple such as acidified dichromate. Only chromium plus 3 acidified permanganate couple Mn2 plus. Then disproportionation and then comproportionation. Disproportionation is defined as a reaction in which oxidation of an element is simultaneously raised and lowered. In other words, the element undergo disproportion can act as the oxidizing agent as well as the reducing agent. That you can see a copper is undergoing disproportionation into copper 2 plus 2 copper. That is a gaining of an electron, that is reduction. Then it will go undergo oxidation. Then the reaction of different of the follows into 2 of reaction, that is copper by gaining an electron that positive 0.52 volts, then copper plus 2 by gaining 1 electron, then 0.16 volts. So 0.36 volts is the difference between from one gaining of an 1 electron to another thing. So different oxidation state. Here the copper has plus 1 oxidation state and then copper has plus 2 oxidation state. Since so 0.3 volt for the disproportionation reaction is spontaneous, this explains why Cu plus is unstable in aqueous solutions. So Cu plus 2 is stable. So in composition, that is the reverse of disproportionation take place. Two species with the same element in different oxidation state form a product in which the element is in its intermediate oxidation state. Example, that is silver plus 2, that will show a positive 1.18 volt. The larger positive potential indicate that silver plus 2 and silver are completely converted into plus 1 oxidation state in aqueous solution at 298 degree centigrade. The redox reaction in aqueous medium, that there are 3 main methods of conducting redox reaction in aqueous solution. Summarizing the thermodynamic stability of the oxidation state of the metal ion in aqueous solution, one is Latimer diagram, another one is Frost diagram, another one is Powerbox diagram. So first two, that is Latimer diagram and the Frost diagram, so these are usually restricted to extremes of a pH 0 to pH 14 solution. Then Powerbox diagram is expressed the variation in stability of the oxidation state as a function of pH between 0 to 14. So what is Latimer diagram? So Latimer diagram will give us idea about when an element exists in several oxidation state, it is convenient to display all of the redox potential for the half reaction in a single electrode potential diagram called Latimer diagram. So in this, the highest oxidation state are written at the left side and the lowest oxidation are at the right of the electrode potential are listed between each species, and the next reduced form and the species such as electrons H plus and then H2O are omitted here. So we cannot see any type of H and the H2O plus. So there is a list of various oxidation state of the element arranged in a decreasing order, that is from the left to right. The numerical values and standard potential is written over a horizontal line connecting species of element in a different oxidation state. and the most oxidized form is at the left, that is higher oxidation state. Then species to the right are in successively lower oxidation state. Then available of all the elements exhibiting more than one oxidation state. So it is an example of an manganese, that is it is showing a various oxidable state from 0, 2, 3, 4, 5, 6, 7, totally 7 different type of oxidation state at 1 molar HCl, that is in the acidic medium. So for the conversion of from 0 to plus 2 by losing 2 electrons, so it will show a redox potential is minus 1.18. so it compresses into shorthand notation all the standard potential for redox reaction of an element, that Mn. So values for multi-electron reaction can be also calculated by first adding delta G naught values and then dividing by the total number of electrons here. So you can see calculating one example that we have taken that calculation of values for multi-electron reaction by first adding delta G naught values and then dividing by the total number of electrons here. So we can know what is the oxidation state of the various metal ion here, that is plus 7, plus 6, plus 5, plus 4, plus 3, plus 2, plus 1. Then for the 5 electron reduction of MnO4 minus to Mn2 plus, MnO4 minus, that is we can write it as a E naught. Then you have to write all the electrode potentials here, then divided by 5, because the oxidation state of MnO4 is plus 7, then Mn plus 2 is 2. So totally 5 different type of oxidations we can come across these two, then that divided by 5, Mn plus 7 to plus 2, then it will show plus 1.51 volts. For the 3 electron reduction of an Mn4 occurs to MnO2, then what will be the oxidation state from plus 7 to plus 4? So you have to write all those things. So the first is 0.564, 0.564, then 0.274, 0.274, 4.27, 4.27. Only these three you want to calculate the 3 electron reduction, then divided by 3, because the oxidation state is 7 in MnO4 minus, and then MnO2, that is MnO2 oxidation state is 4, then divided by 3 the number of electrons, that showing once again a positive oxidation state 1.70 volts. Then thermodynamically we can say the stable or unstable oxidation state by predicting on this value. So unstable species on the Latimer diagram will having a lower standard potential to the left than to the right side, that is 2MnO4 minus MnO2, MnO4 2 minus MnO4 minus 3 is unstable, because a standard electrode potential plus 4.27, 0.274 equal to plus 3.997 volts. So spontaneously it is undergoing disproportionation reaction, which Mn species are unstable with respect to disproportionation, that is plus 5, plus 6 and then plus 4. So stable species are MnO4, MnO2, MnO4 2 minus, Mn2 plus MnO. Thermodynamically unstable ions can be quite stable kinetically. So another example is iron, that iron plus 2, 2. So 4 different type of oxidation state we can see. One is 0, 2, 3, 4. So we are having some values. Then we can also calculate. So it is one of the homework to assign. So which is more stable oxidation state. So this diagram can be used to summarize thermodynamical information about the oxidation state of an element in a convenient way. Then it is very easy to identify the species that reduced. Then potential for the reduction of Fe4 2 minus to Fe plus 3 is positive 2.20 volts, since delta Z for this change will be larger and negative. This means that the reaction is thermodynamically possible, since it releases a large amount of energy, and FeO4 2 minus is a strong oxidizing agent. Then half reaction with negative charge of E naught are strongly reduced than the hydrogen, that is are strongly reduced to E naught value for the changing of an Fe plus 3 to Fe plus 2. Both negative ends delta G is positive, so either Fe plus 3 nor Fe plus 2 have tendency to reduce the iron. Then the Frost diagram. So in this Frost diagram, so we can plot a graph of delta G naught against N E naught. The zero oxidation state is assigned and E naught value is 0 contains the same information as in the Latimer diagram, but graphically show the stable and then oxidizing power. Stable and unstable oxidation state can be easily identified in this plot. So which is stable? So here they have shown some graph. So based on this we can able to predict the stable oxidation state, that is a stable oxidizing number. So here the zero oxidation state is assigned from a 0, so contains same information about a Latimer diagram. So stable and unstable oxidation state can be easily withdrawable. So thermodynamically stable is found at the bottom of the diagram, so it is unstable. So thus a lower species is positioned on the diagram. So from that the thermodynamically we can say the oxidation and then reduction. So any species located on the upper side of the diagram will be a stronger, and then oxidizing state MnO4 is a stronger oxidizer. Any species located at the upper left side of the diagram will be stronger oxidation state, that it is showing a more stronger oxidation state. These part of this are more strong oxidation state. The information obtained from first diagram is a species undergoing standard condition for acidic solution as well as the basic solution. So the last diagram, that is power box diagram, it is a plot of graph E versus pH for various couples in oxidation and then reduction reaction. Then power box diagram is a type of predominant diagram that shows a predominant form element will exist under a given set of environmental conditions. So these diagrams gives a visual representation of the oxidation and the reduction abilities of the major stable component of an environment and corrosive applications. Like frost diagram, power box diagram display thermodynamically preferred species. So how to read this power box diagram? So vertical line separated species that are in acidic medium. Now vertically line separated species. So then horizontal line separated species in redox equilibrium not involving hydrogen or hydroxide ion. So then we should see some diagonal species here. So once again from this we can able to determine the stability of the oxidation state. So once again there is a dashed lines enclosing the particle regions of the stability of an water, solvent and the oxidation and then reduction. So any point on the diagram which will give a thermodynamically more stable from that element at a given potential is at pH condition. Then strong oxidizing and then oxidation conditions can be found at the top of the power box diagram. Then strong oxidizing agent have a lower boundaries that are less higher on the diagram. Then permanent oxidizing agent over all pH, it is very strong oxidizing agent at low pH. So reducing agent and the reduction condition are found at the bottom of the diagram. It is very easy, and the reducing agent having a lower upper boundaries on this diagram, that is manganese.